Alright, so let's take a look at the design of thermometers. I want to explain what we're trying to do, right? So if I give you a thermometer, let's say I give you the one that you have in the lab. Let's say I gave you a mercury in glass thermometer. Right? When I place the thermometer, let's say in something hot, right? What will happen? What will increase? Temperature, right? Temperature in here will increase, right? And what happens here? Right. When you heat the mercury here, right? Because remember, when the mercury goes in here, the mercury will be heated, right? When you heat the mercury will begin to expand, right? The mercury will begin to expand. So the mercury, right? The mercury or the expansion of the mercury varies with temperature. So the expansion of the mercury correct? Right. Right. So when we heat the mercury, the expansion of the mercury varies with temperature. Varies with temperature. Right? This here is called a thermometric property. Right? So the thermometric property of this thermometer is the expansion of mercury. Right? So because whenever we heat mercury, it expands and it varies with expansion based on temperature. We could use mercury in here to help us find temperature. But how does it actually work? How do we know when I heat something and I put it in there, it's 80 or 30 degrees? How do we know that the value is 30 degrees? They create a scale, right? Based on what? Somebody else did in Form 5. We call this calibration of a thermometer. What is it? You remember fixed points, ice points, and steam point, right? So what they do is they place the thermometer and see how it behaves in ice. That'll be a 0 mark. Place the thermometer in steam. That'll be a 100 mark. And then they would divide this by 100. Okay? So when you place it in here, you can easily say, okay, well, it's expanded to the 30-degree mark. You okay with that? Right. This expansion, we assume that these two are proportional and they behave in a linear way, right? So because of that, I could probably get a graph of expansion, or let's call it volume. I could probably get a graph of volume versus temperature. And I'll get a straight line like that. Correct? So if I want, I could create an equation. Can I? I could create an equation that allows me to find temperature based on the volume. That formula that we're going to develop, that's called the empirical formula. Right? So we're actually going to use the empirical formula that could be used for any thermometric property. It can be volume. Anybody know a different thermometric property? What's the next thermometer that we use? Probably can't remember, but you can remember learning about something called a thermocouple. Yeah? A thermocouple is work like this. You have a fixed temperature. You have something unknown. And you take a millivoltmeter and you connect it here and you have a little circuit. So based on your voltage readings, you can work out temperature. So here, for the thermocouple, your thermometric property is voltage. That's okay? Any others? There's a next one called resistance thermometer, right? and that gives you values in ohms. All right. So we're going to take a look at developing the empirical formula. We're going to learn about thermometric properties, and then we're going to look at the next scale. What are the two measurements or two units that we use for temperature? Right. So there's a Celsius scale, that's this one, and there's a next one called Kelvin scale. Right. All right. So let's take a look at it. You know how to write? If it is highlighting important stuff, right? The handout in the group. Right. The rest of this module is just temperature and thermal quantity. Right. These are all these things that we have to do in this module again. Right. We did 6. We have to do 1, 2, 3. Right. And we might do 4 and 5 once we open. And that's the end. Module 3 is a shorter module. It's supposed to be a little bit easier than the others. Module 2 is the more challenging module that we use. Right? So let's run through this here. So design and use of thermometers. The temperature of a body is its degree of hotness. Thus, temperature is a measure of how hot the body is. Thermometers are used to measure temperature, and they utilize a thermometric substance whose property varies continuously with temperature. Can we use any material? Can we use water, for example? Can we use water in a thermometer? No, because water doesn't vary continuously with temperature. Right? You might see the water freeze at 0. You might see it turn to vapor at 100. But between 0 and 100, anything has happened really? Not much. Right? Not much has really happened. All right, so we can't really use water because it's not varying. There's no property that varies with temperature. All right, so we use mercury, and what else? We use something else in thermometers. Alcohol. You remember you may have clinical thermometers at home, right? That only varies in a small range, right? Those are alcohol thermometers. Right, so the physical property is called the thermometric property of a substance. A good thermometric property should always vary continuously with temperature, uniquely over a range of temperature to be measured, and it must be measurable. So you don't want something to expand and you can't measure it. Right? Yeah, that don't make sense. Right? Imagine you're heating the mercury here and it's not expanding. Or it's expanding by such a small value that we can't read it off. Then it's useless, right? So it must be measurable and varies continuously with temperature. Right? Examples of thermometric properties, right? Volume expansion of a liquid. That's the one that we use, laboratory or clinical thermometer. There's a next one called constant volume gas thermometer, where you keep the volume constant and you vary pressure and you read your temperature. Whose law is that? Volume constant, you're varying pressure, and you're reading up temperature. Who? Pressure. Right? Right? You have to remember those laws, right? Because we're going to use them too. You all did the ideal gas equation in chemistry. Yeah, we do the same thing in physics. But how was it? How was it? Huh? 10 people do. Huh? Ideal gas. No, we're going to do. Ideal gas, you probably use somebody in development. Like PV then I would see. Well, I can put it next one. Right, next one. Constant volume gas thermometer, change in pressure. Thermocouple, change in EMF. What EMF? Adam, all right? Huh? Electromotive force is really what? It's really voltage, right? It's really voltage. Resistance thermometer is the resistance thermometer measures the electrical resistance. So any one of these here, 1, 2, 3, 4, any one of these is a thermometric property, right? And we can use any one of these to find temperature. All right? We need to remember fixed points. What are the 3 fixed points? People doing chemistry. Emma. What are the 3 fixed points? Upper, lower, and what? Get up one more. All right, let's see. Right? The single temperature at which it can be confidently, it can confidently be expected that a particular physical event always takes place is referred to as a fixed point. So we expect to see ice at the idle point. We expect to see steam at the steam point. What's the triple point? It's an extremely unique temperature at which all 3 phases exist: solid, liquid, and steam. Anybody guess where you might observe this? What? Which one? Something like something similar, right? But you could sort of experience triple point above a pond. There's a particular point in time when the pond will be liquid, ice on top, and you have water vapor being released on top of the ice. Right? And that particular temperature is called the triple point. Right? But it's very difficult to observe because it must be observed at a particular pressure. All right? Unlike the other 2 observed at atmospheric pressure. Right? Let's run over ice point. Ice point is a temperature at which pure ice can exist in equilibrium with water and standard atmospheric pressure. It is used at 0 degrees Celsius. Steam point, temperature at which pure water can exist in equilibrium with its vapor, is called, 100 degrees Celsius. And this one here, which is new to everybody, right? The triple point of water is the unique temperature at which pure ice, pure water, and pure water vapor can exist together in equilibrium. It is used as 0.01 degrees Celsius. The triple point can only occur at a special pressure, right? So this special pressure must happen. That's the only way you can observe a tree, right? 611.2 pascals. Right? Something that's a little bit new in CAPE is that in order for us to work out Celsius, we have to use 273.15. We no longer use 273. We use 273.15. Right? Anybody can guess what's the triple point in Kelvin? What's the triple point in Kelvin? Yeah, get your calculator. What's the triple point in Kelvin? What's the ice point in Kelvin? 273.15. What is the steam point in Kelvin? 373.15. But what's the triple point in Kelvin? Yep, 273.16. Triple point is 0.01. Right? Do me a favor. Write that down. It was the first time I heard of my life. But I might never open this handout again. Write down the 3 in Kelvin. These are all the we are doing just set up temperature. Module 3 temperature. Huh? First, second. For one to look what's in. Huh? You have nobody get PD class. After pay off nobody. No. So when I leave, get it clean out. I have class now. Okay, but if have nobody else, I stop leave now. I'm good. Let's think of those down. How is this look? It's I how it works. Last part. Just take it back. You know, it's all the thing. Just so so money can just get from. Right, so triple point, we write down on 3, right? Right, so 273.16, that's the triple point. 273.15, that's the ice point. 373.15, that's the steam point. All right, next. On the Celsius scale, right, we know that already, right? Right, so what you see now? Right, that things we get in the thermodynamic scale here. Right, an interval of Kelvin is defined as being 1/273.16 of temperature of the triple point of water, right? And we see the triple point of water here, right? Right, yeah, so an interval of Kelvin is defined as being 1/273.16 of the temperature of the triple point of water as measured on the thermodynamic scale of temperature, which gives this. So what you're seeing here, we call this the thermodynamic scale. This is the scale that will give you temperature in Kelvin. So if they ask you to use thermodynamic scale, that's what you're using there. PT is the pressure of the ideal gas, and PTR is the pressure at unknown at triple point.
That's one. Giving you my phone, that's one. You don't know what the second one is, please.
Right, so make a note of that, please. Thermodynamic scale equals to that formula. Right, so in order for us to find temperature on the thermodynamic scale, we need pressure at the unknown temperature. We need pressure at the triple point, and then you look down. Quick question: Is this formula dependent on any thermometric property? What do you think? Is it? What do you think? No. I'll say it. Adam. Wait a second. Yes or no? Is it dependent on any thermometric property? No. All you're doing is just reading up pressure. All you're doing is just reading up the pressure at a particular temperature. That's it. So it's not like a pressure thermometer you use, right? You just reading up pressure. So you read out pressure at the unknown temperature, and then you read out pressure at the triple point. Right? So you're just reading up pressure values. You're reading up pressure values. That's all. Right? Just write down what is PT and PTR so you'll know when you're using it. Right? So note that the thermodynamic scale of temperature is totally independent of properties of any particular substance. Right? There's no substance there. All we read know is the pressure values, right? So we call it the absolute scale. So if a question says, what's the absolute scale? This one's the absolute scale, right? So let's just practice using it now. Try this, please. Try this here. Ready? A gas thermometer. A gas thermometer, constant volume. A gas thermometer at constant volume has a pressure of 100 kilopascals. A gas thermometer at constant volume has a pressure of 100 kilopascals at the triple point of water. 100 kilopascals at the triple point of water. Man, 100 kilopascals. 100 kilopascals at the triple point of water. Full stop. At another temperature, the pressure is at another temperature. The pressure is at another temperature. The pressure is 150 kilopascals. Find the temperature. Find the unknown temperature in Kelvin. That's simple. Plug it in. Just plug it in and work it out. Please use 273.16 earlier. Go rounding off, right? How much you all got? Hey, Joseph. Where you going? Where you going? Hey, go ahead. Go ahead. Tell me answer one time. How much you got? 5.9. Much all you got? Yeah, 409.7, right? What you do, right? Right, so we're using this formula here, right? Think of 100 over 150. The 100 over 150 or 150 over. Right, so 150 over. It was 150 over 100 multiplied by. It's supposed to be 400 and what? 409.7. That could work. Yeah. Right. Last one. Try this last one here. Number 2, a constant volume gas thermometer. A constant volume gas thermometer has a pressure of a constant volume gas thermometer has a pressure of 101.3 kilopascals. 101.3 kilopascals. At the triple point of water. When the gas is at a temperature of 455 Kelvin, when the gas is at a temperature of 455 Kelvin, calculate the pressure of the gas. Calculate the pressure of the gas. 455 Kelvin. 455 Kelvin. Find the temperature of the gas. Sorry, find the pressure of the gas. Take your time, rearrange and solve it. Find the pressure of the gas. Right, if I move this here, anybody recognize it? I'll move it on this side. Anybody recognize this? What's that? Pressure low. Right, pressure low. So this whole fancy formula here is pressure low. Right? The temperature they gave us is 455. Pressure at the unknown temperature, we're trying to find that. And pressure at triple point is 101.3. Right. If I use 101.3, it means that your answer will be in kilo. All right. So if you leave it like this, your answer will be in kilopascals. If not, you had to put by 10 to the 3 here, right? So cross multiply, it will be 455 by 101.3. This by this is this, divided by this. What's up? How much? 168.7 kilopascal. Right? So that's basically how we use the thermodynamic scale. All our temperatures will be in Kelvin. Now we're going to take a look at the empirical scale. All right? Everything right there in the notes, but I want to show you, it's a little proof at the beginning, I didn't know there. Actually, there's something that you have to do, but I'll help you out here. If we look here, we could use this little graph here, right? I'll do it on board. We could use this graph. I left out the value because I wanted you to figure it out. But we could use this graph to help come up with the empirical formula. All right? So the empirical formula is used to find temperature in degrees Celsius. The absolute formula, or the thermodynamic here, that is used to find temperature in Kelvin. All right? So let's take a look at the empirical formula, right? In order for us to do the empirical formula, we need a little graph. Oh, wait. Sorry, online. Sorry, they're online. Right, let's use length. I think I gave it in length. Let's use length in meters, temperature in degrees Celsius. Right? Huh? I used to volume my formula. L. No, the next one. In the notes, I think I use L. Right? So this is the temperature at 0 degrees Celsius. At 100 degrees Celsius, this is the length. Let's call this L0. Let's call this the length at 100. That's okay? So we're going to develop a formula from this. Everybody remember how to find gradient, right? Gradient is what? Y2 minus Y1 over X2 minus X1. So we're trying to come up with a formula that will help us find theta. So theta corresponds to L theta, right? So we are trying to generate a formula that helps us find theta. That's okay? Right. Step number 1. Let's see if we could find gradient using 2 sets of points. Let's see if we can find gradient using this point and this point. You see that? That point there is what? 0, L0. And this point here is what? Theta, L theta. So let's find gradient using that. Gradient is Y2 minus Y1 all over X2 minus X1. Right? But we can't leave it equal to gradient, so we have to find an next gradient. So let's use here and here. Right? Let's use 0, L0. And 100, L100. So gradient is now equal to L100 minus L0 all over 100 minus. You okay with that? Now you gotta do the fun part. Make them equal and make theta this subject. Make them equal and make theta this subject. Yes, make both of them equal. And this is gradient. And this is also gradient. So make them equal and make theta the subject of the problem. Let's do it again. Make them equal and make theta the subject of the problem. You will graph up, right? Because this is not in the hand of it. You will the graph. Remember, the objective is to make theta the subject, right? Because we have to use this to find temperature. Ready? So you just you're just going to equate them, right? So you'll get L0, L theta minus L0 all over theta plus theta minus 0 theta is equal to L100 all over 100. I want to make theta the subject, so I'm just going to cross multiply. Right? So when I multiply this by this, I get this by this, I get this. So theta is L theta minus L0 all over L100 minus L0 by 100. This is your empirical formula. All right? This is the empirical formula. So what do we need? We need the length of the column at the unknown temperature. We need the length of the column at 0 degrees, length of the column at 100 degrees. All right? This could be anything, any thermometric property you want. This could be volume, this could be resistance, this could be EMF, pressure, anything. Right? It could be anything. Right? So make sure you know what each letter means, right? Length at unknown temperature, length at ice point, length at steam point. You okay with that? So how you know when to use this formula? When they say empirical or they say temperature in Celsius. Then if they say thermodynamic or temperature in Kelvin, you use that one bit. Plus you'll also see what they give you. If you see triple point, you're using that. No triple point, you're using it. Okay? Let's try a few. You gotta remember heat capacity and thing. I'll go over it. Right, there was heat and heat capacity and percentage heat capacity. Try this please. Right? Write this down. A constant volume gas thermometer. A constant volume gas thermometer. Yeah, question one. A constant volume gas thermometer. How many people have access to ChatGPT? P.com. P.com. You all use that? So if you're using the free account, you also use custom chatbots. You all have access to that? No, there's something free, man. There's something free right next to it. Yeah? Right. So what I'm doing, right? You recognize as the users all the time. What I do is I'll be putting in questions and ask it to keep making up. Like if you're practicing, you can go to the custom bot and ask it to make questions for you, and then it'll correct it for you after. Yeah. But I don't know if it's on the free version. But I have to give you a link to the bot I just trained. So that bot will only give you a CSEC and case type question. Yeah, let's train it to give you the type of questions that I want to give you. No, all you do is just put in this and put in exam type questions and it will give you. So like when you're practicing, they'll give you a question and the answer. Right? So I'll give you access to it like later on. Right? And you just do the question and you have the answer, you can practice. Right? And check back your answer. And the more you practice and I correct it, it will make mistakes. Right? Try this one here now. A constant volume gas thermometer has pressure at 0 degrees. Pressure at 0 degrees. Hold up. Pressure at 0 degrees, 92 kilopascals, 92 kilopascals, 92 kilopascals, 92 kilopascals. A constant volume gas thermometer has pressure at 0 degrees, comma, well, equal to 92 kilopascals, and at 100 degrees Celsius, and at 100 degrees Celsius, pressure is 148 kilopascals. Find the unknown temperature. Find the unknown temperature find the unknown temperature in degrees Celsius, of course. In degrees Celsius, when its pressure is 116 kilopascals, 116 kilopascals. 116. Right? So real simple, you just plug it in here. Plug in your pressure, unknown pressure, 0, pressure at 100, pressure at 0. Right? Don't forget to multiply by 100 out. And your temperature will be in degrees Celsius, right? I never use it, but people say go take it for finding paper or something. Huh? Like what? Anyway. But try it and use it, the more they use it, the better. So that. Huh? But I see them using it as fine paper or something. He's not in class. Tell him he should be in class. Which class? I see other line somewhere. You know, you online? I think it. Fire Pukogora. Prayers now I there. Long sleep, where that's it? Yeah, try it and see. We're having the same thing. Sorry, what? I don't know what I'm ground bouncing. Here. That's what I need. When I had to use that stuff. Gotta get the values. Keep breaking up, keep breaking. Yes, it's a Right, what you all got for this first one here? So it's P theta minus P0 over P100. Right? What was the pressure at P theta? Pressure here is what? 116. Pressure at 0. 148. Right? And then you'll get a temperature, which was 4. Anybody else get up? Yeah? Good. Let's change the word in slightly. Number two, a resistance thermometer has R0 as 40 ohms, R100, right? That's the resistance at steam, ice and at steam, right? As 90 ohms. All right, 40 and 90. The resist, first up, next line. Next line, the resistance of an unknown temperature is 30% of the way. The resistance of an unknown temperature is 30% of the way from R0 to R100. From R0 to R100. Calculate the temperature in degrees Celsius. Calculate the temperature in degrees Celsius. Try that there. So it's 30% anyway, right? Right? So when they say 30% of the way, right? Between here and here, it's somewhere in between here, right? It's 30% of the way between 40 and 90. Right? So we have R0, R100, we need R theta. That's a big problem, right? So there are different ways that we could find it. The difference between these two is how much? 50, right? So all we need to get is where is 30% of 50. That will cancel, that will give you that, and that will give 15. So 15 ohms down the road. So that looks like 40 plus 15, which is 55 ohms. Right? So R theta is 55 ohms. Now, how do we find theta? Same formula. Please get in the habit of writing it like this. R, because it's resistance. R theta minus R0 over R100 minus R0. Right? So that will be 55 minus 40 all over 90 minus 40. How much is that? How much? 30? 30 degrees Celsius. All right? So that's the way you do empirical formula, right? Let's do one from a past paper and then we go back to things on Form 5, right? I think that was the next thing. Try this one here, please, at the time over here. Usual problem. Part B we're doing, right? Part B is starting here. Part 1 and 2, right? Just part 1 and 2. How about? You find it enough? Let's try saying what? Finish? No. Right, so you're gonna help. Right, help more there. So our resistance thermometer is placed in a liquid at 0 and pump temperature. So tell me what its value is here, R what?
R0. Oh, R0. That's the question.
3750 is what? R what? R0. 215 is what? R what? And 950 is what? The one letter misses, don't tell him nothing, huh? R what? R unknown, R theta. Yeah, everything you need. You have everything you need there to find theta. You have everything you need to find that new temperature. Work it out and then part 2 and see if we can figure out why. Well done. We have theta, right? So you'll get theta is equal to 3750. Oh wait, no, that's wrong. Right, our theta is 950. Right, our 0 is 3750. Our 100 was 215. Once you get any chance? 79 point. That's what I get, right? 79.2. All right, nice. Now do it the other way. So now here's what happened. And I'll pick on Ethan. The reading taken at the same time in a mercury glass thermometer, they got 76 instead. Suggest one reason for the difference. So why the resistance thermometer not precise? You want to help him? So why the values different? A mercury in glass thermometer got 76 and our resistance thermometer got 79. We don't know which one more precise, right? But why the difference? Think about what makes them different. What makes them different? Huh? One measuring expansion and one measuring resistance. So, what do you think causing the possible difference there? 76 and 79. Right. The way the thermometric property behaves temperature, they both will behave exactly the same. Right? So they both might have a straight line graph, but one might be slope a little bit more than the next. Right? So different thermometric properties vary slightly. All right, make a note of that. One difference for the reading is that the thermometric properties vary slightly with temperature. The thermometric properties vary slightly with change in temperature or temperature change. Right? So again, we didn't technically talk about this, right? But I wanted to learn in an exam how to figure these things out. Right? So you had to look at, okay, what's the difference between both of them? One is mercury, one is sister. What causing them to be different? Right? It's kind of hard to say one is more precise than the next. Right? So I wanted to learn, okay, so what are the main things that changing and see what I come up with. All right. The next one we can do another. All right, so that's the two types of temperature, thermodynamic scale and the empirical scale. All right. The next thing that we have to redo is stuff from Form 5. Right, so I'll bring somebody up on the board to go over everything. Right? Head up, wait, I want to bang the hand up. Hold on, some of these things that start, I'm still have to do them so long. Now, this just have heat transfer. Oh yes, there's something I talk about internal energy. Chemistry people, what's internal energy? What's internal energy? So if I ask you what's the internal energy of a system, I would like to know what's how the particles behave in there, right? How the particles contribute into kinetic energy and potential energy. Okay? So the internal energy of a system is the sum of the kinetic and potential energy. Right? In the system. If the internal energy, the internal energy can be increased by doing work, right? And applying heat. That makes sense? Sure. If you do work on it, you will increase potential. If you apply heat, you will increase kinetic. Internal energy involves energy on the microscopic scale. For an ideal monoatomic means one atom gas, right? Internal energy is entirely translational kinetic. What that means is the gas, the particles so far apart that they don't have the one between them real weak. So their energy is mainly kinetic. Only kinetic. Right? And they have rotational and vibrational kinetic energies. In liquids and gases, there is a potential energy associated with the intermolecular activity. If you look at this little diagram here, it shows you for gas is purely kinetic, right? For molecular gas, it have a little rotational Y. Why a molecular gas has vibrational and rotational energy, while an atomic gas doesn't. And of course, well, you can see solid and liquid, right? A lot of bonds between them, so you have potential energy. But yeah, that was green cloud. Where that come out from? Still a gas, right? What y'all think? What's the difference between molecular and atomic? So atomic. Sort of molecular means that probably have more than one, like hydrogen, H and H, right? So you have two particles. So those particles have slight bonding and they rotate as they move, right? So that's why molecular gas has that little green region. All right. So good. So it's important we understand internal energy. We're not going to use it now. We're going to use it in thermodynamics. All right. All right. Before we do heat transfer, I want to talk about a thing from Form 5. Let's talk about those things, right? Let's see if you remember this. Let's say I gave you a block of ice. Right? When you apply heat to this ice, what could happen to it? What will happen to it? It could change temperature. So it could change phase. And it could also change temperature. So in order for something to undergo a temperature change, it needs energy. Right? Anybody remember how to find the energy? Right, MC delta theta. C is your specific heat capacity. Right, that's the amount of heat required to change the temperature of a particular mass. And then, if something underwent a phase change, it's equal to what? MLH, right? LH is your latent heat. Right? So this is what we use: temperature change, phase change. Sorry, phase change, temperature change. Right? We also have something called heat capacity. We also have something called heat capacity, uppercase C, which is M by small c. Right? Or energy required to change the temperature of something. All right? So we need to remember these small things from form 5. That's okay? Also, to find energy, energy is equal to power by time. Power could be VI by T. So we need to remember these two things as well to find energy. All right? Try that in. Right? So we need to remember those small things, right? Right, so in form 5, we would have also done modes of heat transfer: conduction, convection, and radiation. Now we're going to apply formulas to all of that. Right down there. Checking cupboard. Huh? You can write it. Temperature change. Oh, this is energy. Right, that's the question you do there earlier. They want you to find the specific latent heat of fusion of material. And that's all they give you a graph. Right? So this is how they would give it to you in keep. They give you a graph and you gotta figure out from that graph how you're getting those things. How we're getting latent heat of fusion and material. Our next part two now. Let's see if we can do on part two. Specific latent heat of fusion of the material. Right, so that's all you have, nothing else. I have nothing else to offer. Sorry. You have no values underneath something. They give you a graph. So you have to figure out how that graph can help you. I don't know. Once you find latent heat of Got you? Gotcha. Let's see what you have now. He said that a graph on figure 7 shows the first an experiment which is in which a crystalline material is heated at a constant rate. So it means constant rate means you have the same power being delivered right through. Right? You have the same energy delivered per unit time. So they said now the material now is at 85. And the liquid is heated to 110. Yeah, no, but I don't. The specific heat capacity of the crystalline state is 430. Right? So all they did, which part is crystalline earlier? Which part is crystalline? From where to where? From 85 to 110. No, it melted there. Wait. So tell me what happened in here when temperature staying the same? Change in phase, right? So that it should be what? Melting there. So if you figure out where is melting, where is if you figure out where is melting, where is it crystalline? Here. Underneath on top. Underneath. And where is it liquid?
Oh.
Where is it liquid? On top? Okay? So, what's the man right? So, they gave us the specific heat capacity during crystalline state. Right? And they said the same heat is being supplied all the time. Any ideas what we can do? Look at what they give you. We know for sure. How do we find latent heat of fusion? That you want to find that, right? So what's the formula? E over M. Very good. E over M. We don't know E and we don't know M. So we have to find out we take E and M. Right?
Oh.
Try something. I don't want to help you. I might have to. Okay, we have 5 minutes. Right. All here. Okay.
No, but it's no. Right, so it comes from. Oh.
Can you see right, but what? Right. You don't go là it lasted 50 seconds. Freedom United States. Right? So you pick up sour, pick up power. If you use the pathway, right? Look at what it gave us. It gave us E, sorry, it gave us C is equal to 1. If you use C is equal to 2. If you find it power, we can I want to give it, yeah. So you can put those. Yeah. What hands they go pick it up. That was okay. So somebody asked this, right? He said, well, he cares what? Energy is equal to power by time. Right? Because he wants to get his energy here. Right? Energy is power by time. But we need to find a way to get, we know the time, right? We know it took 15 seconds here. That's okay, right? But we don't know the power being delivered. So, what about trying to figure out the power being delivered here? right? Power is what? Energy divided by time. Correct? Power is energy divided by time. What's the energy being delivered there? That's a temperature change, right? That's a temperature change. So the energy formula is what? M C delta theta all over T. Do we know M? No. Do we know C? Yeah, and that's 430. Okay, what's it up here? Do we know the temperature change? Yes, 85. And do we know how long it was heated for? 0 to 50, which is 50 seconds. You see now? So now, what do we have? I can work out this here. How much is that? What's that? Was 430 by 85 and 50. How much? 731. So I know that power is 731 by 10. That's okay? Power is 731 by 10. Now, I can use that power here. See what happens? So I know the power being delivered in terms of mass. No, we don't know mass, right? But when it's substitute, what do you think will happen to mass? Cancel out. Yeah, because they both have the same mass. Right? So in short, those two get lost. Right? During the temperature change, I use the quantities they gave us to find the power being delivered. Right? And the power being delivered was 731 by the mass. So since the same power being delivered during all the phases, I can use that value now. Right? I can use that value. See what you get now? I say remember you're coming back here, right? That's where you use it. Define header. Right? Energy is what again? Energy is power by time over the mass. What's the power? Power is 731 M. What's the time? 15 seconds. All divided by mass. The mass will cancel. The mass will cancel and you will get
10,000, I don't know.
10,965. What's the SI units? Joules per kilogram.
Okay.
Okay. No temperature change. Well, you got 10,965, right? All right. Still have one more part. But you'll figure it out. The last part is the one, the specific heat capacity in the liquid phase. Can you do that? Do it fast, Gilbert. Find the specific heat capacity in the liquid phase. That's much easier. Specific heat capacity in the liquid phase.
Nah, it's absolutely.
We think about
I think you have something about it. This was like 150.
right, find that and we done.
I was starting. No.
Right, Ashad, how we find and C here? C is equal to what? E over M delta theta, right? And we know energy is power by time. What we use it for power? 731 M, and time is how much here now? 55. All over M. And what is temperature change? 25. 85 minus 110, right? Cancel up there. What you all got? What you all got there?
1608.
How much?
1608.
1608.2. I was doing calculations. So I was doing calculations. Finish already? 2 minutes. How much work? What's somebody? Right, yes. All right. Well done. All right, nice. Take a little break. Take well done. Take well done. I will still give you up to 16 minutes, right? 16 minutes.